Hello everyone, my name is Borui-Battery. I'm from Oak Ridge National Laboratory. My presentation is a battery equivalent model and load flexibility analysis of commercial refrigeration system. Now I start presentation. The outline. This presentation includes research background, objective, system and operation assumptions. And the most important is the battery equivalent model and assumptions. And it ends with the conclusion and the future works. As we know, existing buildings can be considered as distributed energy resources by using their embedded storage to provide grid services. There are multiple research studies about different kinds of building loads, including AC load, while our team recently focused on the power flexibility research of a commercial refrigeration system. This is the control schematic of the commercial refrigeration system. For given air temperature set point and the acceptable diet band, the cooling is turned on when the case air temperature deviates from the set point, while the temperature of the refrigerant in the display case evaporator is typically sub-zero. This will ultimately block the airflow and dramatically reduce the cooling capacity. To handle this issue, regular defrost cycles are needed after a period of normal control. During the defrost period, the refrigerant flow maintains off and the temperature keeps increasing until it reaches the maximum allowed temperature. It's followed by a recovery period when cooling capacity is delivered again. So we can see that the normal operations often last 4 to 10 hours, while the defrost periods last around 40 to 60 minutes in real cases. And for the recovery periods, it's only about 20 to 40 minutes. Research motivation. In US, the commercial refrigeration system accounts for more than half of total energy consumption in the supermarket and superstore. And there's a significant amount of thermal mass in the frozen food to store the energy, thermal energy, and the shift thermal energy. So in addition, compared with the traditional HVAC system, refrigeration system have several unique features. For example, as I just explained, each display case has to go over defrost cycle per day, and the initial status has a quite large impact on the power performance. But few studies develop battery equivalent model and analyze the power and the energy flexibility of such a system. The objective, we first developed control-oriented models for both compressor and display cases. We develop a general and standard battery equivalent model for the individual commercial refrigeration system with some assumptions. Such a BEM can characterize and quantify the aggregated flexibility from multiple systems, and it also help the grid operator to better understanding the building load. For example, such multiple types of building loads can be treated similarly as electric battery, and there's no much need for the grid operator to consider the diverse characteristic and dynamics of individual building loads. So in a word, BEM can facilitate the development of a commercial refrigeration system as a flexible distributed energy resource through bridging the gap between utilities, company, and the customers. This is one typical system located in Oak Ridge National Laboratory, and it was designed by our researchers. It includes medium temperature as well as low temperature display cases, and accordingly compressors. We can see there are two sides of compressors. These are the four figures for two kinds of display cases and two kinds of compressors, two sides of compressors, we can see. And this is the basic information about the compressors and the others display cases. There are two fixed speed and one variable speed compressors for medium display cases, while there are only one fixed speed and one variable speed for low temperature display cases. The detailed values of these parameters are listed in this table. Similar to the typical building RC model, we develop RC model as well for both kinds of display cases. The model can reflect the thermostatus and the response of the air encase, the frozen food, and the display's temperature, display case itself. Both medium temperature and the low temperature display case are models with the same equations, but the ranges of the parameters are different. Because the searching process for the optimal value of these undetermined parameters in this model is a kind of a nonlinear optimization process. So we use the PSO, particle swarm optimization, to search the minimal room mean square errors of both T air and T frozen food in the objective function. The room mean square error is also used as the index to evaluate the model performance. We can see that the developed RC model can have good performance in prediction of the air temperature and the frozen food temperature. We also use simplified regression method for the compressors. And the inputs include saturation, suction, and discharge temperatures for these models. We can see that there are two sides of regression parameters, A1 to A11, B1 to B11. The resulted parameter values are listed in these two figures. And we can see from these figures that the calibration performance is quite good. And these figures indicate that we can generate high level accuracy from the developed simplified models. We also validate the whole system, which integrates both display case and compressor models. We select only one single day, and we set the low temperature display case defrost 1 time per day, while the medium temperature case defrost 6 times per day. The measured case air temperature and the power consumption in both kind display case are compared with the simulation result. We can see the first figure is about the validation of the air temperature prediction for the low temperature case. In the most of the time of the whole day, the display case is under boundary feedback control. The air temperature ranges from -5 Fahrenheit to 0 Fahrenheit. This one defrost period, which is lasting around 14 minutes, and then it follows by a short recovery period. The corresponding power consumption is this upper right figure. And we can see like the left two figures show the temperature and the power validation of medium temperature cases. One main difference is that there are 6 defrost periods in the whole day for the medium temperature case. And in summary, the simulated low temperature case can achieve, low temperature system can achieve good performance in prediction of both temperature and power, while the medium temperature case system the simulated air temperature can capture the trend of the measured temperature, while we can see that it's lost the fluctuation in the original measured temperature profile. Based on the above simplified model for display cases and compressors, we can develop a battery equivalent model by converting the format and making some assumption as well. These figures show the schematic. The right line is the profile of the air temperature, which is commonly available to characterize the instantaneous capacity, namely the SOC, the state of charge of BEM. During a normal period, if the temperature reaches the lower value, which is the side point, it means that the status is fully charged at this moment, and the SOC is 100%. If the temperature reaches the upper boundary, which means that the status is partially discharged, while during the defrost period, the temperature keeps increasing until it reaches the allowed maximum temperature. This state of charge is 0 at this point, and then it starts falling down during recovery period, and the whole cycle repeat again. We made some important equations for BEM. As you can see, we define SOC in this equation, and the T psi is the side point of the air temperature, and the T max is the maximum allowed temperature during defrost period. And this equation is used to represent the overall cooling energy stored in the display cases. The CL is the lumping capacity of air within the case, which is resulted by the RC model. These two equations can deduce equation 6 and learn substitute equation 1 in the RC model to finally get the equation 8. As we can see, equation 8 includes charge and discharge power efficiency. Actually, the efficiency is just the COP of the compressor and the thermal loss part, which is from the RC model. We made some important assumptions. First, the thermal state of charge is equivalent to the electric state of charge, and learn the maximum charge and discharge electric energy are equivalent. The max charge electric energy is fixed temporarily, but we know that actually it's not. It should have some variation along with the change of weather condition and the initial status. At last, both temperature and electric power increase or decrease linearly. So these are the results. The SOC fluctuates 0 to 0.8 to 1 during normal conditions period, while it reduced to 0 when the temperature reaches the top value during defrost period. And we can also see that the SOC and the charge electric energy follow the same pattern because we use a dynamic SOC to multiply the fixed maximum electrical energy value. So the results are good. And the conclusions. The BEM can be very critical for comparing and aggregating the capacity of different commercial refrigeration systems with quite different characteristics. And it can also help to extrapolate the ability to perform further more great services. And one major difference from the real electric battery is that such a kind of BEM, their discharge and charge power and energies are almost determined by the weather condition and the initial status as well. In the future, we will consider more realistic conditions. For example, maximum charge and discharge electric energy are not equivalent. Meanwhile, both temperature and power profile are not linear and not mirror symmetrical. So the SOC is not the same as the electrical SOC. Therefore, we need to do more detailed modeling work to generate more accurate BEM. Thanks. That's all.